Hi guys, welcome back to another video, and in this video we're going to be creating a parser in C++. This video is the second video of the series of compiler development videos, and I was supposed to upload this video yesterday, but this video got delayed for some reasons. But anyway, so let's get started. So there is a prerequisite for this video. You need to understand what grammar is in the context of computer science. So grammar is basically how using grammar is basically how we would define the rules for our parser. And I have this image over here. This basically is there are actually four types of grammar: type 0, 1, 2, and 3. This all these four types come under the hierarchy of Chomsky. It's I think his name was Noam Chomsky or something. So he was a linguistic who designed the formal way of classification of grammar. So there are four types: type 0, 1, 2, and 3. uh, I don't think you need to, for our purposes, you don't need to understand in depth the concept of type 0 or type 1 or type 3. What we need is the type 2 grammar or the context free grammar. So basically, a context free grammar is the type of grammar which is used by a parser or which is used by a compiler to check the syntax of the program or of the source code which we have submitted to the compiler, and also to generate the abstract nodes, the abstract syntax tree nodes. So that being said, I'll just show you a little bit. Talking about parsers, there are two kinds of parsers: a top-down parser and a bottom-up parser. A bottom-up parser is also called a shift-reduce parser. And the top-down parser has a further classification of two types: backtracking and no backtracking. And within the no backtracking classification, we have further two types: a recursive descent parser and a predictive parser. So basically, when we write a parser by hand, we write a recursive descent parser. And when we want to generate a parser using YACC or something, there are many other tools. Probably the most famous, or the tool which I know, is YACC to generate parsers. They basically use algorithms to generate the parser, and some of the algorithms are LL1, LLK, LR0, SLR1, and so on. So we are going to be writing a recursive descent parser. And what that is, before knowing that, I'll give you a gist of what a context free grammar is, because our parser is going to be using the context free grammar for parsing. So I'll just make a new file over here. So basically, how we define grammar is, or I'll just make it CFG, which stands for context free grammar. So basically, any kind of grammar, not only context free grammar, any type of grammar consists of something which is called as production rules. So production rules have two things within them. Basically, production rules are the rules which define the generation of grammar, and they have two things within them. First is the LHS, and then we have an arrow symbol, then we have the RHS. And to give you a very brief gist of what these production rules are, you can of course look it up on proper tutorials on context free grammar. There is one channel called as Neso Academy. I watched their videos to learn about context free grammar, so you could check them out. But giving you, so basically, the things that we have in a production rule can be classified into two categories. First, we have the terminals, then we have the non-terminals. And terminals are written in small characters, while as non-terminals are written in big characters. So to give you an example of how this would work is, let's say we have a non-terminal called as sport. So sport can generate a non-terminal can generate a terminal, but a terminal cannot generate a non-terminal. So defining sport as a non-terminal, the terminals for sport could be cricket, and instead of comma we could use this sign. I think it's called a pipe sign, but a sport can be either a cricket or a football or whatever, a tennis maybe. So this is how grammar works. We have a non-terminal sport which has the ability to generate any one of the terminals: cricket, football, or tennis. To make this more clear, let's just add another terminal over here. So a sport can be of non-ball type, and a non-ball sport can either be, I don't know, swimming or racing, I don't know. So this is how grammar works. We have a non-terminal on the LHS which has the ability to generate a set of terminals or a non-terminal, and that non-terminal further has the ability to generate terminals. So for more understanding about this topic, you can refer to the online resources, because this video isn't about actually context-free grammar, But anyways, I gave you a very brief introduction about it. We just need to make sure that the grammar or the context-free grammar that we define for a parser is free of two things, which is called as number one, left recursion, and number two, non-determinism. So I'll explain what these are. So I'll have a sample grammar over here. Let's say we have a statement. So let's say we have a non-terminal statement which has the ability to generate, let's say, a print statement maybe, or let's say it has the ability to generate an exit statement, or it has the ability to generate a statement. So what we could do is, if we write this as this, have a grammar which says that we have a statement which has the ability to generate another statement itself or an exit statement. So basically this is an example of left recursion, because if we write this programmatically, this would be, if I write the pseudocode of the parser for this grammar, this would be I don't know, func statement, and then within this we'll again make a call to the statement function. So basically this would end in an infinite loop. So this shouldn't be here. Instead, this should be on the right hand side. So this is basically what is called as left recursion. To get rid of this, we should basically push it to the right hand side. And the second type of thing which we should not have in our grammar is non-determinism. If a while back I explained you the type of parsers, so the two types in the top-down parsers were the parsers which have backtracking and the parsers which do not have backtracking. So in the recursive descent parser, there is no option for backtracking. So I'll give you an example over here what non-determinism is. Non-determinism is basically not having the ability to overcome backtracking. So let's say we want to generate AX. Let's say we want to generate AX from our grammar, and let's say this is our source and we want to generate AX from our grammar. So basically let's assume S can generate A, and then A can generate A and X, let's say, or A and Y, or A and Z, and then X can generate small x, and Y can just generate Y, and Z can generate Z, capital Z can generate terminal Z. So if we have this grammar is non-deterministic. Let's say we have to generate AZ. So what would happen is, once we generate, once this goes into the grammar, we generate A. Now A can either be AX or AY or AZ. So now AZ is over here. So now let's say if we are in this segment of the code, or in this segment of the parser, so we would have to check for each of these three segments, but the only thing we want is over here. So we would need to backtrack. Once we check for this, we would need to backtrack, and then we would need to check for this. Then again, since AY is not equal to AZ, basically AY would produce A small y using this rule, but since AY is not equal to AZ, we would again need to backtrack, and you would need to move to this production rule. So to avoid this, we use the concept of left factoring. Left factoring is just basically taking out the leftmost common stuff. So we could just take this out and just put this over here. And now our grammar is not non-deterministic, and now we could avoid backtracking. We need to only make sure that our grammar is free from these two stuff. And after that, I don't think there is any kind of error which could creep into our grammar. So the grammar which we are going to be writing for our program is going to be simple, because it's the start of the program. So I'm going to be writing grammar for declaring variables, printing stuff, and returning stuff. So now let's name this grammar pilot CFG. And basically what else I'm going to be doing is the non-terminals for our grammar, I'm going to be wrapping them around angle brackets, because I also want to show how we incorporate our tokens. This would be more clear when we write this. Basically, we would first have a source, and the source would yield a bunch of statements, and function is called as the clean star. This basically means that it can yield any number of statements. The statement can either be id is equal to, we have to put the arrow over here, can either be id is equal to expression, or it could be return, and we need to put semicolon over here, or it could be return expression, or it could be just print, and within the brackets we would have the expression and then a semicolon. Then the expression can be an int, or it can be an ID, because we could also print let's say x. So x is a variable or an ID. So this is what we have for now, but actually I want to just make it as int for now. When we'll incorporate variables in our further videos, then I'll change the grammar accordingly. So we could just essentially put int over here in all these three places, but this just makes it more versatile, and this makes it more versatile and easy to edit. So if we want to like add ID in the future, we could just do this, but I'll just keep it this for now. So this is the grammar for our parser. So now let's keep this into account and write the parser. So we'll create a new header file. So this is what we had made in the previous video. So let's just run this and see what's happening. We could just tokenize this. Okay, I want to edit the build task again, because I don't want to like run pilot.cpp again and again, pilot.exe again and again. So configure default build. Okay, so once we compile this, we do a pipe, because in PowerShell we use pipe. In CMD we could append multiple comments using double ampersand, but in PowerShell we use the pipe symbol. And then we clear the screen, and then we do another pipe, and then we do dot / pilot, and then we supply the name example.py. Let's save this. Let's see if it's working or not. Okay, so we aren't in PowerShell, I believe. We are in PowerShell, so I don't know why this is happening. Let's just build this again. Oh, it's working now. So we didn't need to put that. So this is what we had. This is what our program was. Let me just clear the screen again and run this. So we were just tokenizing it, and then we were receiving a bunch of tokens. Another thing which I wanted to first do before we start writing the parser is I want the return to not be an ID, but I want a return to be a separate token type, which should be keyword. So first I'm going to make that, and I also want to append an end of file token at the end. So first we make the token keyword, and then so first we want to do two things. First we want to make the token keyword, then we want to append the end of file. So first we need to check here. I think this was the token as ID function. So this function is being called for anything which could this function could be called for either ID or keyword. So we could just do tokenize ID underscore keyword, and then ID underscore keyword. So now let's first of all define a series of keywords. So we'll use a vector of string, and we call this as keywords, and this would be this return for now, and let's also do print. So We could just use a ternary operator over here. I think I saw this in Stack Overflow. We could first import algorithm. Okay, include algorithm, sorry. And then what we could do over here is we want to, okay, there you go. We want to check whether the buffer is in the set of keywords or not, and if it is, the token type would not be token ID, it would be token keyword, else the token type would be token ID. So what we would do is we would do std find, and we'll find from keywords.begin, I believe, or start keywords.begin, okay, begin to keywords.end, and we'll find the buffer to str, and if this is not equal to keywords.end, then we could just do, if this is not equal to keywords.end, then it means that we have it in the keywords vector. So the token type would then be keyword, else the token type would be ID. So I think this should work. So we find from the begin to the end the str, and if it is not there, so if it not reach the end, it's the keyword, else it's the ID. So this should work. I think we need to make some changes over here, and also in the enum type, I believe. No, the enum type is fine. So we need to write a case for this. So case token keyword, we'll just return token keyword. I think we are good to go. So let's save and run this. Okay, so we are not getting this for some reason. So it turns out that our build command is not configured properly for some reason. So I'll just get rid of this and I'll save this. So let's compile this and I'll just run it manually, I guess. There you go, it's working now. So there was something wrong with the build command. So we are getting the return as token keyword. Let me just check everything else is right or not. So we have token ID equals int semicolon, another ID equals int semicolon, then we have a token keyword, left parenthesis, token ID, right parenthesis and semicolon. I think I want to get rid of the parenthesis for now. I don't think I have that defined in our grammar also. So I'll just get rid of this. And I don't think we even need a parenthesis in return because we're going to be returning this one value. Even if you're going to be returning like a bunch of values, you could just append a comma at the end. So like number 1, comma number 2, return number 1, comma number 2. But that's something which would be done way later. We need to just first write a simple parser now. Let me save this and build this and run this again. So yeah, return is a token keyword and this is token ID and it's semicolon. Just to make sure this shouldn't be a keyword, this should be an ID. So let's see. It's an ID, so it's working properly. Now I just want to append an end of file token at the end. So have we defined end of file? No, we haven't defined the end of file token. So token end of file, it's not over here also, I believe. So case this, we'll return this, and while we are generating the tokens, I believe I think we need to write a case for when we encounter the ASCII value 0, or yeah, we could just do 0. We do token end of file. This should take care of it, I believe. Let's build this. Let's clear the screen first, and we're not getting the end of file for some reason. Okay, that's not the purpose of this video. That's a very silly bug which I can fix later. So let's do something. Let's just right now we'll just check the end of the tokens, and if we have an end of file, if we do not have an end of file, we'll just append one. It's a very ad hoc and a very terrible solution for this, but it's a very simple bug to fix, a silly bug to fix. We have to just spend a bit more time, but that's not the purpose of this video, so I'll just write this ad hoc solution. So how do we do this now? So we'll just do if tokens dot back. I think we do use a back type is not equal to token EOF. Then I think we need to create a new node. So token pointer, okay, token pointer new node is equal to, let's call it EOF node to make it more verbose, more easy to read. New token EOF node is equal to new token. And the reason why the sound of the keyboard is changing is because I'm switching between my laptop's keyboard. So this is my laptop's keyboard. So this is my laptop's keyboard, and this is the keyboard, another external keyboard which I'm using. So this one is the mechanical keyboard. I think this is the blue switch. I don't know. I think it's the blue switch, the clicky sound one. So that's why. So EOF node, and the type of this would be token EOF. I don't think we need any kind of value, so we'll just push this. So tokens dot pushback, and we'll push the EOF node. I think this should work now. So let's build this. No errors. Let's run this. It's working now. I think I want to print the source code, because why aren't we printing the source code? It would be more easy to read, because else I'll have to open it over here. So let's just do let's just make this on another line, I believe. We do the source code, then another line. Let's build this. Okay, we need another new line over here, and also at the beginning. Yeah, so this is the source code. So I don't like the way this looks, so I'll just make this number underscore 2. Let's run this again. Okay, we need to build. I don't think we need to build this. I don't know why I built it again, but anyways, let's clear the screen, and this is the source code. So number 1 is token ID, token equals token int semicolon, token ID equals int semicolon, return as the token keyword, and then number 1 is the token ID, and then we have a semicolon, then we have an EOF token. Great. Let's just do something. Let's just, for the sake of testing, let's just introduce this. Let's see what's happening. Okay, there you go. It isn't a parser error. The code is right, but I have done some, there you go, a very silly mistake. It's a Lexer error. So let me just, there you go, Lexer error. So it's working properly now. Let me just save this. I don't know, pilot CFG, yeah. And let's just remove this and make sure everything is working fine once again. There you go. So I think our the Lexer was ready. The two things which we had to take care of are done. So now let's actually get started with writing the parser file. We'll call it parser.hpp. We'll do the if not defined thing. Uh, parser underscore h. We would define the parser underscore h, and then we'll do endf. Okay, so using the approach of object oriented programming which we had taken for the Lexer over here, where's the Lexer? Here you go. So I want to similarly call the parser, and to the parser we'll supply the source, we'll supply the vector of tokens, and yeah. So first of all, I make the class parser. I use this keyboard. Okay, class parser, and we define the constructor. The constructor won't return anything, but it would take in the input of a vector of pointer to tokens, and we call them as tokens. And I think I need to include a bunch of things. First I want to include the Lexer, then I want to include vector. Should give me no errors now. There you go. So I forgot to write the public and the private stuff. So this would be public, and within the private block we would have, what would we have? We would have first the int limit. Basically this would be the maximum number of tokens, the token limit basically. Int index, and we'll have a current which would be a pointer to token. So token pointer current. And do I just take a reference of the tokens, or okay, just not to complicate things. I was thinking to like not make a copy of this, just to pass this by reference like this, and but I won't do this now. So we'll just make a copy of it. So we'll do std vector of token type. Let's call this as parser tokens. So we'll have all these four stuff. So first we just do parser tokens is equal to tokens. Parser tokens is equal to tokens, and index would be 0. The limit would be parser tokens dot size, and the current would be parser token dot add index, I believe. So yeah, we have our constructor for parser ready. So we need to define an abstract syntax tree structure for our parser. One thing I forgot to mention, which I should have mentioned at the starting of this video, is basically what does a parser do? It uses the context-free grammar to validate the syntax of the source code. It also constructs an abstract tree node. It also constructs an abstract syntax tree. So basically, we first give the source code to the Lexer. The Lexer would generate a bunch of tokens, and the bunch of tokens, when goes to the parser makes use of the context-free grammar, and given the bunch of tokens follow the grammar, it would construct an abstract syntax tree. So we need to define the structure of the nodes of the abstract syntax tree. So we would need to define the structure of the nodes of the abstract syntax tree. So we'll do struct ast node. Just write this over here. And first, I want to do an enum node type. So enum, just like we did in the tokens, node type. So a node can be ID, The node can be, the keyword types have two classifications if we refer to our grammar. So it can be either return or print. So it can be a return node or a print node. Then we also have a node for integers. I think these 4 nodes are enough for now. Yeah, I think so. So we'll just do an enum node type and call it as type. And what these would have is, we also need a root node, of course. The root node would be the node we would give to our, basically the root of the abstract syntax tree. And the root node is what we'll pass to our assembly generator. So node underscore root. So now we need to define, I think we need to put a comma over here. So now we need to define what we'll have in the AST node structure. So we'll have the node type, and then we would also have, basically we would have the value of the node, I believe. The value would be, how do we do this? Let's make it a string. Let's make it a pointer to the string. Because let's say we have the ID number 1. The number 1 is already in the memory, so we'll just reference to it. It isn't optimized from the perspective of, like, since all these data is like scattered around the memory, so the CPU would have to load something from there and something from very far apart. So from that perspective, it isn't very optimized, but we won't do any kind of premature optimization. First, we want to get stuff ready. So it will have a value. Then it would have a child. So it would be a pointer to the abstract syntax tree node pointer, and we'll call this as child. And we'll have, for the case of root, for the case of the root node, we'll have a vector of pointers to AST nodes, which would contain all of the statements. So I'll just use this approach for now. So AST node pointer, and what should we call this? Substatements, I believe. I don't know. Yeah, this is only for the root node. So we have the structure for our AST node ready. I'm a bit skeptical about this, but I think it's good for now. So let's do the parse function. So what I want to do here is, in the pilot.cpp file, we have over here, just like we declared an object of the Lexer class. I think I need to import it first. Include it first, not import it, include it. So we include the parser header file, and we create over here, we would create a parser object. So parser, let's call it parser, and we'll supply the tokens. Then what we would do is, we would have the root node. So AST node pointer root would be something which we get when we run the parser.parse function. So this is the syntax which I have. Of course, this isn't root is undefined. Okay, I don't know, but we have to define the parse function. So let's get started with that. So I'll just comment this out, and in the parser function we'll do AST node pointer parse, and then we would first create a root pointer. So AST node is not a type name. Okay, so do we get rid of this? Maybe. Okay. So maybe that's why this wasn't Like the only error should have been here. Okay, since we have written the parser file, that's not even an error, but the parser function. So anyways, so now first we declare the root node. So we'll do ast node pointer, call this as root is equal to, should I make it in all caps? Okay, equal to a new ast node, and if we do, the root type should of course be node root. And what else do we have? The type is done. We don't need a value for it, I believe. Neither do we need children. We just need to push the nodes. Push basically this the stuff into this vector. So I think we have this ready. We'll just do a return root, because I always forget to return the root, or return basically from such functions. So now what we'll do is we'll do while I think we had this in the current. Okay, yeah. So while current, I think first we need to make a proceed function. So what the proceed function would do is, it's similar to the peek function which we had, but it would also check for the grammar. So I'll just first write it down. Then it would take in an enum type. I think it will take in, what's it called? The type of the token. It's called type. Okay. Enum type, I believe. Is this wrong for some reason? No, it isn't. Okay. Yeah. So it will take an enum type. So let's say that we want to verify ID is equal to int. So once we know that this is an ID, we need to proceed, but we also need to make sure that the next thing that we have is an equal sign. So basically, you would pass the ID or pass the type of what we want to be checked over here. And if it matches, then we'll proceed and we'll return the pointer to the next token, else we'll throw a syntax error. So this is basically how a parser works. A recursive descent parser works. So what we'll do is if current type is not equal to type, or let's do it in caps. If the current type is not equal to type, then we'll throw a syntax error. There is something wrong with my mouse pad, but anyways, do we do a syntax error or a parser error? Okay, we'll do a parser error. Let's do syntax error. Syntax error. And okay, there is some issue over here. Okay, let's just I don't know, make it small. Yeah, it should be working now. And we'll just do an end line and we exit. Else what we'll do is, I think we would just need to increment our index, yeah. And the current would be equal to, why is it throwing an error? Okay, the current would be equal to parser tokens dot at index, and then we'll return the current. Yeah, there is something wrong over here. Are we including the Lexer file? We are including the Lexer file. Okay, we have to do enum type, and let's put this should work. So we have our proceed function ready, and now what we'll do is in the parse function we will switch on the we won't do a switch. Okay, we'll do a while loop while I think current and the type is not equal to the end of file, while the current type is not equal to end of file. Again, then we'll do switch, and we switch upon the current type. And okay, so now we need to refer with our grammar. So basically the statement can have an ID in the starting, or it can have a keyword at the beginning. So we need to write two functions, the parse ID and the parse keyword. So if we have a case for token ID, I believe, what we'll do is we'll do root substatements dot pushback, and we would call the parse ID. So this would basically the parse ID would be a function which would return an AST node, and then we would break. We need to define this, of course. Yeah, I think it's good for now. Do we remove the parenthesis? Okay. And if it is a keyword, then what we'll do is we will do parse keyword, and then we'll break. And I think after this we would proceed with because once we are done with, let's say, this, we'll be with a semicolon, or once we are done with this or this, we would have a semicolon at the end. Like once we're done with this, we'll have a semicolon at the end. So we need to proceed with the token semicolon. Okay. And I think we need to have a default case over here. Yeah. We need to have a default case over here, which would be std cout, and again we'll throw up a syntax. I think I could just copy this entire thing. I could just wrap this around a function and call this again and again, but it's okay. So I think this is good enough. So now let's define the parse ID and the parse keyword. So first we have the parse ID. The parse ID would return an AST node pointer, parse ID. And first we copy the value. So we don't copy it, we just keep a reference to it. We don't need to just copy stuff around. We call it the buffer, and we'll just copy whatever is at the current not the type, the value, I believe. Yeah. And after that, I think we need to proceed with token ID. Okay, we need to proceed with token ID, and then after the ID, according to our grammar, we need to have an equal sign. So we need to again proceed with a token equals, and after that we would be left with the expression. So we need to parse that. So we need to basically call the function for it, but I'll first make a new node. So AST node new node is equal to new AST node, and the new node it will have a type of okay, we have a node. No, we have a node ID. I want to call it node variable now, so we'll just do variable variable. The type would be node variable. What else do we need? We don't need the root. The type is variable. Okay, the type is variable. We wrote the value. We don't need the substatements, and the child would be a node end. So that's how we do it. So child would be, we would do parse int. Actually, with reference to our grammar, we should be doing the name of the function should be parse expression. But since the only expression that we have right now is an integer, so I think we'll just do this for now. We'll edit this later. So the parse int would return a pointer to AST node, which would be the child of the new node which we are creating. So we need to define this also. So parse int, and I think that would be good. And we'll just return this. So we'll just do return new node. Okay. So our parse ID function is ready. I think we first do the parse int function. AST node pointer parse integer. So we also need to make sure that the thing which we have right now is an integer, not like anything else. So what we could do is we could just do it manually for now. If current type is not equal to token int. Okay, 1 second. Yeah, we need to copy that again. Syntax error. And I know the syntax error that we are throwing right now is probably the most vague syntax error. Actually, in the 1 second, I copied this again. I saw a video online. Basically, what that guy was doing is that in the proceed function, where is the proceed function? Yeah. So if the type is not, if the current type is not equal to the type which we are expecting, we'll do a syntax error. And then he was writing that unexpected token current type expected type. So we could do it, but I'll do it later. Yeah, I'll do it later. So we were here, we were passing the integer. So if the current type is not token int, we throw a syntax error. Else, I don't think we need an else case. So we create a new node. We create a new node, and the new node's type should be node int, and the new node's, not the type, the new node's, the value, I believe the value should be, I think we need to pass a pointer, right? Yeah, we need to pass the pointer. So we need, so we'll just pass the address of current value, and we'll just return. Okay, why is this an error now? Okay, it's not an error. We'll return the new node, and I think our integer passing should be working now. Yeah. So the parse ID function, which is dependent on the parse integer function, is working now. So we need to write the parse keyword function. Okay. So do I copy this? Okay, let me just write it again. Parse keyword. And I think this function should branch onto other functions depending upon the type of keyword. So like if we have a return keyword, If we have a return keyword, then it should call the parse return. Else, if we have a print keyword, it should call parse print. And apparently, you cannot do switch case based upon strings in C++. So we would do this by if else. So if the current value is equal to return, what we'll return from the parse keyword is the stuff that we'll get from parse return. And we'll do else if current value is equal to print, we will return what we'll get from the parse print. This is being highlighted for some reason. Okay, since we only have two keywords, I think this is enough for now. We'll just throw a cautionary else case over here. Else we'll do std cout. Do we copy and paste this again? I think over here we could just also write syntax error, undefined keyword. Yeah, I was just checking the spelling. So it's good for now. And now we need to write the parse return and the parse print function. So ast node pointer parse return. And just letting you know, the reason this process of writing okay, so there is some error because everything got highlighted over here. So I'll just remove this here. So what I was saying is, the reason the way we write parsers like this is called recursive descent is basically, it would be clear to you by now, because we are basically switching on the type of the current tokens type. And if we have a token ID, we call the parse ID function. And okay, let's take the example of this. If we have the token keyword, we call the parse keyword function. In the parse keyword, depending upon the value of the current token, would call the parse return and the parse print function. And while we write the parse return function or the parse print function, these two functions would also call the parse. And so we recursively call parsing functions to basically parse our tokens into a bunch of AST nodes. So this is the reason why this is called as recursive descent parser. So we had the AST node pointer called as parse return, and I think we first proceed with token keyword. Then what do we need to do is we need to create a new keyword. I think after proceeding with the token keyword, if we refer to a grammar, we should have an expression. So let's first create the AST node pointer new node is equal to a new AST node, and the new node, the type of the new node should be node return, the return node. And I think, yeah, the child of the new node should be the parse int. We don't need a value, I believe. No, we don't need the value, we don't need substatements. The type is done, we need the child, and the child should be parse int. And once we have proceeded with the token keyword, what we should have is the expression. So yeah, we're making sure of that. We should have the integer, not the expression, because we are doing this for integer right now. So we are making sure of that. So I think this should work. I just realized this is so big, I could just make this small. But anyways, so the parse return function should be working now. We need to return the new node, of course, and the node return parse int. Yeah, I think it's working. And we do the same thing for AST node pointer parse print. Yeah, think I think it's okay. For the parse print function, we would need to make sure of these two brackets also. So first of all, we do just copy this. We would just proceed with the parse print keyword. Let me just copy this entire thing. I could have just copied the entire, even the function definition, but it's okay. The type would be node print, and since we proceeded with this, we would have to proceed with the left bracket. So token, do we have a left parenthesis? Yes, we have. Then we do this parse int. Are we proceeding in the parse int? I think after this is done, we should proceed. Because okay, id is equals to, and yeah, I think we need to proceed. And once we proceed with the integer there, uh, once we proceed, where is the, okay, we need to minimize this and this. Yeah, so once we proceed with the integer there, we should proceed with the right parenthesis, and we are proceeding with the semicolon over here. I think it should be working if we proceed with the right parenthesis. So we do proceed token right parenthesis, and then we return the new node. I think this should be working. I think so. So let me just save this. I actually would be surprised if this just worked on the first run, which I'm pretty sure it won't, but we did build it. But let's see. We are getting a syntax error for some reason. Why are we getting the syntax error? We did follow the grammar, right? It would be embarrassing if I described the grammar myself and I didn't follow it. We have a token id equals. Okay, so let me just refer back to my parser. I'll just drink some water. My neck's very dry. Okay, while the current type is not end of file. I don't think this is right. This has to be token end of file. So that's the first bug. So we switch the current type. In case we get the ID, I think let's just see where is this syntax error message creeping from. Let's do 1, 2. There are better ways to do it, but I'm very lethargic, so I'll just do it this way. Let's build this, and let's clear the screen, and now let's run this. 2, okay. While we are passing the integer, okay. Is it because we're not proceeding from the id function? We are proceeding from the id function. Token equals, then we need a token integer. Token id equals an integer. Oh, because that's why. Because according to our grammar, we can only return an expression, and an expression can be an integer. But over here, we are returning a number. So that's very embarrassing that my language isn't even following my grammar. But anyways, so if we run this again, there you go. So it's working. I believe it's working now. So if I do if I do the size of this root, size of the substatements of root, so I think we should be getting 3 because there are 3 executions, there are 3 statements over here. So let's just check it. So let's just do std, and I'll just remove before I forget. Where is it? I'll just remove these 3, 2, 1 messages. Yeah, and we'll just do std cout. This is the number of statements, and we'll do root substatements dot size. Let's add an end line over here. Let's build this. This should be 3. There you go. There are 3 statements. And if I just copy this and paste, okay. If I just let's just save this. So this would have 2 statements. And if I just do return 6, this should have 7 statements. Okay. So now let's see whether this program is actually checking our grammar or not. So let's not print this, and let's not get this either. Okay, I want to do another thing. If I just do this, this should also return 3. This should return 3. There you go. So okay, I don't want this to be printed right now. Tokenize successfully, okay, but I don't want to print this. Let me just build this, and I just want to make sure that the error checking is working correctly or not. Okay, I'll just make this end. Okay, anyways, so I don't know what happened over here. I'll just do another terminal, and we'll do /pilot. Wow, can never spell properly when I'm recording. Pilot example.py. So we are getting the number of statements and we are tokenized successfully, but what I want to check is whether we encounter any kind of syntax error or not. So I'll just remove this message also, and I'll remove this extra whatever new line. I should just make use of escape sequences to print new line again and again. Okay, the build is finished. Now let's clear and run this. So yeah, so now if we are getting over here, we could just print let's do std cout no syntax error, and we'll do a new line over here. Okay, it has to be like this. Alright, no syntax error. But if I let's just put this like this and run it again, no syntax error. Should I just append a clear at the start? Okay, yeah. So no syntax error right now, but if I forget this semicolon, this should return a syntax error, right? And if I start this off with an underscore, this shouldn't be a syntax error because we can start with an underscore, yeah. But if I start with a number, this should be a syntax error, right? So let's just do this. In the previous video, I had given you the example of the differences of the errors that we encounter in the Lexer and the Parser. So my alarm is ringing for some reason. So in the previous video, I had shown you an example of the differences which we get in the errors in a Lexer and a parser. So let's do 1 for 1 is equal to number 1. So both of these statements are valid for the Lexer, but in the previous video I had said that this statement would be invalid for the parser. So if I save this and I run this again, there you go, syntax error. Because we cannot, the grammar is that a variable should be equal to an integer, not an integer should be equal to a variable. So if I just do number 2 should be equal to 141, there should be no errors right now, no syntax error. If I just forget this, I'm just trying all permutations, no syntax error, syntax error, and no syntax error. If I do this, since return with a capital starting capital R is not a keyword, this should be a syntax error, I believe. If I do this, syntax error, right? And if I don't return anything, syntax error, there you go. I think our parser is now ready. I just want to try out with this syntax error, and if I just put this, there shouldn't be any syntax error, no syntax error. So our parser is ready. So in the next video, we'll write an assembly code generator, and I'll probably switch to Linux. I'll probably switch to my Kali machine, because it turns out that while we are doing this in Windows, the only way to write proper assembly is that we either link this with a C file or we make use of the Windows API. And I want to do neither of the two options, so we would just switch to Linux. So our operating system would then run on Linux. So our operating system would then run on Linux, but that's not an issue. So in the next video, we'll write the assembly generator. So I'll just commit this entire thing, this entire file to my GitHub. The link would be in the source, so you can check it out. And thanks for watching, guys. And yeah, bye-bye. Thanks.